Welcome to example number 1. We're asked to determine the energy in joules and the wavelength in nanometers for a photon that would excite a hydrogen atom from n equals 2 to n equals 7 state. So the first thing we need to do is figure out what the energies are at those two specific states. Remember that the energy in general for a hydrogen atom is negative 13.6 electron volts divided by n squared. So if we were to look at the excited state of n equals 2, our energy would be equal to negative 13.6 electron volts divided by 2 squared. This gives us an energy of negative 3.4 electron volts. This is also listed on the energy level diagram that's in your previous page of the notes. N equals 7. So we're going to be plugging in E sub 7, negative 13.6 electron volts divided by 7 squared. And this gives you a value of negative 0.27, we'll just have to round it off to 278 electron volts. So if we're looking for the amount of energy that is required by the photon, we're going to need to find the energy, this is energy of photon here, is equal to the energy difference between these two levels. So that would be the difference between these two levels here. So we're going to take E sub 7 and subtract E sub 2 from it, and the energy of that photon will be equal to negative 0.278 electron volts roughly, minus 3.4 electron volts. And this will give you an energy of 3.12 electron volts. So that's the amount of energy that you'd have to have coming, that certain specific amount. Now, we want to know what it is in joules, so we're going to convert this electron volt to joules by multiplying by 1.6 to the power negative 19 joules for every electron volt. And we get about 4.9959, well, let me just round this off to 5 times 10 to the power of negative 19 joules. And there's our energy of the photon. Okay, now to find the wavelength of the photon, remember the energy of a photon can be calculated a lot of ways. H times F, hc divided by lambda. Oh, we want the wavelength, so let's use this one. So we're going to rearrange for the wavelength, and we're going to have hc, that's Planck's constant sine of the speed of light, divided by the energy. Now, there's a lot of ways you can do this, using the energy in joules if you'd like, or you can use the electron volts. We've got a difference of 3.12. Let's use that, 3.12 electron volts. Now, for HC, you need to pick the right value. If you look above the notes, remember, there's a lot of ways that you can use for HC. And take a look at the different values. You could use H as this in electron volts seconds. There is even one in your notes, I believe, or in your formula sheet for HC. And I believe it is, let me just take a look over here, it's 1.24 times 10 to the power of 3 electron volts times nanometers. And this is very nice because you already get an answer. The electron volts cancel out, and you'll get an answer in nanometers. And so you'll get a wavelength of 397 nanometers. Now, if you use other values for H and C, sometimes with the rounded values, you may not get exactly what is listed as the answer here, because there will be a small difference between it. Okay, that's it for example number 2. Or sorry, example number 1. You can move on to example number 2 now.